when you access the iClass, a pop-up window Adobe Flash Player settings appears on your screen. It wants access to the camera microphone on your computer, so you click on Allow, and then you click on Join Audio.
The only person in this conference.
So, so far we are the only person in the virtual class. You are the educator. Now we wait for the student to join in. So we now see that the student has joined. So that is the student over here in the users window. So we'll now go through the main buttons and features of the virtual class, how to use this virtual class to deliver a lecture or a seminar. We take a look at the top left hand corner of the screen and we see this icon, Share My Desktop. This you can use to share your desktop and share any presentations or slides or software that you have on your computer that you want to show to the audience. But this particular button is much more suitable for countries or regions where they have very good broadband internet. The next button is to share my microphone. This we have already done. When we access the iClass, we already shared the microphone, so we'll not click on that again. Now, if you want to show your face to the audience, you can click on share my camera so that they can see you. You can do this either before class or at the end of class. Now we move on to the Zestiness window. So we see that all those who are listening in, who have the audio connected, so that's the educator and that is the student. And we now see here that at this point they are muted. We mute them so that in the course of the lecture that there's no outside sound that can disturb the class. Okay. Now the next window we'll take a look at is the chat window, which is in the right hand side. So this is the chat window. So I'll write a message here that to the audience that welcome to the lecture, and I will add you all set, and we'll wait for the student's response. So the student will write that they are ready. So we see that the student has said that yes, I'm ready for the lecture. So once you know that everyone is in the class, then you can now start the lecture. Or to start the lecture, we take a look at this button on the bottom left hand side of the default presentation slide. So here we see here it says upload a document for presentation. So we click on that and then we click on browse file. So we look for the folder that our lecture is in. So my folder is lecture notes. Then I click on my lecture notes for today, which is educator_lecture. And then I click on upload file. So I click on upload file, it converts it into the format for the server. And we wait while it loads. So it's loaded now. Now we see that it's not very clear. So we move to this button here, which means to fit to width. So we click on fit to width and then it makes it much more clearer. So this will make the lecture slide much more clearer. It's a high resolution for the students to be able to see. So you can now start going through the lecture. So in this paper, we will give a self-contained demonstration of the following two theorems. So the first theorem is theorem 1.1, let G be a compact Lie group with a Z-invariant metric. Assume that with this metric, G is positively curved. Then G is diffeomorphic to S3, which is same as SU2, or G is diffeomorphic to SO2. And then we also prove this theorem, theorem 1.2, that if G is a compact Lie group, then G has a bi-invariant metric. And further, with only bivariant metric, G has non-negative curvature. So then you can then begin to go through the lecture slide. But in case you want to annotate or make a point, you come here and you click on this button here on the bottom right hand corner. So I'll click on this button. This button gives you access to the whiteboard. So I move up and I click on the highlighter. I click on the highlighter. Then I begin to write with my electronic pen from the graphics pen tablet that I have. So I'll begin to write here. So I will begin to write, and I can annotate the document here. So say we will prove two important theorems today. Two important theorems today. Okay. So the electronic pen of your graphics tablet allows you to annotate the document once you choose the highlighter option of the whiteboard. So then we can begin to go through the definitions and preliminaries. If you want to underline anything, you can underline that. This definition 2.1 is extremely important for us to note. You can put a star by it. This is extremely important. And you can say, now let's look at definition 2.2. So the use of the electronic pen of the graphics tablet allows you to annotate your document as you go through your lecture. But in case you want to give a traditional lecture where you write without showing slide presentations, you can also do that. So to demonstrate that, what we will do is that we will again go to upload document for presentation. So again, I do that here. Then I click on browse file, and then this time I'll click on TBE lecture template. So this is a series of blank PowerPoint slides that I can write on. So I click on that, and I click on open, and then again I click on my upload button. So it's uploaded now, and we see as it loads, so the blank slides are uploaded. Again, I click on fit to width so that it would make it bigger for the students to go to clearly see it. So today's lecture is on metrics on compact Lie groups. But before we would do that, we would want to give a short review of the concept of the derivative of a covariant tensor field on a Riemannian manifold. So that is what we will first take a look at. So I click on to go to the next slide, and then with my electronic pen I can begin to write. So we will be looking at the differentiation of covariant tensor fields. That is the topic that we'll review before we study metrics on compact Lie groups. Now, let phi be a covariant tensor field. So phi is a covariant tensor field of order R on a Riemannian manifold. We see that this is all in real time. So the students are seeing everything as we're writing here on the Riemannian manifold M. Manifold M. Okay. Recall that for the covariant derivative of a vector field so vector field x, we used the notion of parallel transport. So I move on to the next slide and I begin to write. We used the notion of parallel transport of a vector field, or parallel transport of a vector field. Transport can come here of a vector field. Okay, so we define the parallel transport of a vector field as follows. Now we let P of t be, for simplicity, we take a C-infinity curve on the manifold M. Okay. Now we let P of t naught be a fixed point on the curve. Now we define the parallel transport tau of t from t p of t naught, and which is a tangent space at the point p of t naught, to the tangent space at any general point t p of t m on the manifold. So p of t is just any general point on the C-infinity curve, while t p of t naught is the tangent space at the point p of t naught, where p of t naught is a fixed point on the curve. Now let us draw a picture to illustrate this. So we imagine we have our manifold M. So this is our manifold M. I have my C-infinity curve, P of t. Now I fix the point P of t naught, and then I take any general other point P of t on the curve. So using this, we now define the derivative of the covariant tensor field phi along P of t. So we now define the derivative of phi along the C-infinity curve P of t. So we define that as follows: that we define that the phi over the t, we use the same notation that we use for the covariant derivative of a vector field. This we define as the limit. So we have here defined as the limit. So the covariant derivative dphi over t evaluated at the point t naught, since p of t naught is a fixed point on our curve, as t goes to t naught, of 1 over t minus t naught of tau t star of phi p of t minus phi p of t naught, into brackets here. So this is the derivative of the covariant tensor field of order r along the C-infinity curve P of t. The curve doesn't have to be C-infinity. We can weaken the condition to it has to be at least C1. But just for simplicity, we use the fact that the curve is the C-infinity curve. Okay. So now let's see whether the student has any question to ask so far. Based upon what we have done so far, we have now defined the derivative of a covariant tensor field along a C-infinity curve. We want to find out whether the student has a question. So we see that the student has raised their hand because we see the hand icon right by the student. So we know that the student has a question to ask. So then once we see that, we can then unmute the student for the student to ask the question. So we can unmute the students. So the students here, unmute the student. So
You are now unmuted.
So we see that the student has a question to ask because they clicked on the raise hand icon, and we can see it's right by the student. And now, since the student doesn't want to talk, they decide to write in the chat, as we can see here. As the student is write write a message in the chat. So we see that the student has written, educator, what is tau star? Because they don't want to talk, they could talk by unmuting themselves, or you could unmute them and then they could talk and ask their question. But in this case, the student wants to use the chat window to ask what does tau t star mean. So then what I'll do is I will explain what that means. So to do that, I will move on to the next slide and explain what this means. Okay. We will now explain what tau t star means. Okay. So recall that we defined tau t. This was a power transport. It went from t p of t naught m to t p of t m. Now, tau t star is the pullback map. We used it when we also talked about the covariant derivative of vector fields. Now, what it does is that it acts on the tangent space at t p of t m. This is a very rough, this one a very precise definition. It's a very rough definition. And then it goes into the tangent space t p of t naught m. So when we apply the pullback map, tau t star, to the covariant derivative, the covariant tensor field evaluated at the point p of t, so this. Now its value at the point p of t naught is found this way. So we take the values. So these are x1 through xr. These are vector fields at on tp of t naught. So this is defined is equal to phi evaluated at p of t, and then its argument is tau, right, tau t, and then we write a lower case, so subscript star x1, and we go on until we get to tau t, tau t, and then we have star x r. We have this. Yeah. Now this tau t lowercase or subscript star, this is the differential of the power transport map tau of t. So this is how we define the pullback map when it acts on covariant tensor fields. So this is a crucial ingredient in the definition of the derivative of the covariant tensor field. So the student now writes a message. So the student has written a message that thank you, I understand it now. Then we can now continue with the lecture. So here we'll end here by saying that the notion of the covariant derivative of the tensor field, or the derivative of a tensor field, is very important, because when we consider the Riemann curvature tensor, where we have R of x, y, z, w. Now, when the phi over the t when the R over the T is equal to 0, we say that the Riemann curvature tensor is parallel. This is a very important property that we will further explore next week, because we will prove a really nice theorem by Catan that says that if the Riemann curvature tensor is parallel, then the Riemann manifold is a locally symmetric space. This is a very interesting result that relates the derivative of a covariant tensor field. In this case, the covariant tensor field we take a look at is the Riemann curvature tensor. And it relates it to an important property of a space. It tells us that if the Riemann curvature tensor for a space has a zero derivative, then the space is locally symmetric. So this will end today's lecture, and we will continue next week. So I can type in a message here. Thank you for attending to this lecture. At this point, I can unmute all the students by clicking on the unmute button, so they can just talk informally. And then once I'm done, I click on send. So thank you for attending to this lecture. And then I come here and I click on the logout button. So click on the logout button logs me out of the lecture. So I click on that.
Only person in this conference.
And then, so it takes me to the homepage for transborder educators. So this is the way an educator would use the iClass to give an online lecture. So this ends today's presentation then. Thank you.